In this video, we are going to take another look at stellar magnitude and we will be studying the different type of spectra that are produced by objects in space. We will start by considering the different ways that light can interact with matter. For this class you will be taking a closer look at how light is emitted by heated material, how it is absorbed, refracted, reflected, and diffracted. The last one is important. We see spectra of light emitted by objects due to the way their light is diffracted. The color, wavelength, of light emitted depends on the transitions of electrons from an excited state back to their ground state. Electrons can be boosted multiple energy levels and each transition back to their ground state involves different amounts of energy. The more energy involved, the shorter the wavelength. Each transition produces a line in the atom spectrum. Since atoms of different elements have different numbers of electrons, each element has a unique spectrum, like a fingerprint. In this image, the blue block absorbs blue light and reflects the others. The black cube absorbs all light and reflects none. The white absorbs none and reflects all. Light is bent when it passes from one material into another. This is because it changes speed. The amount the speed changes depends on the wavelength of the light. Try this demo. Fill a clear glass 1/2 full with water. Stick a pencil in the glass. How does the pencil look? It should appear bent. Depending on the material being heated, different light sources give off different colors of light. Mercury vapor lamps are bluer, sodium, or halogen lamps, are yellower. And, true neon lamps are a vivid red-orange in color. Mercury vapor lamps give off more short-wave radiation, and neon lamps give off more long-wave radiation. Diffraction gratings are glass or plastic that has been engraved with very closely spaced lines. These grooves diffract, or spread out, the light into the wavelengths it is made of. Rainbow viewing glasses are a common example of something that uses this material. Spectroscopes, used by astronomers, also use diffraction gratings. Another place where you may have noticed diffraction of light is off your CDs or DVDs. If you are interested, you can get directions of how to build a simple spectroscope using a diffraction grating and serial box from the Stereo Mission website. We will be using spectroscopes in class to look at the spectrum produced by different light sources. There are 3 types of spectra that can be produced by different physical processes. Exactly what produces each of these types of spectra will be covered in upcoming slides. Light from a hot object gives off a continuous spectrum. If light from this object passes through cooler low-pressure gas, some wavelengths are absorbed, producing a dark line or absorption spectrum. A low-pressure gas, excited by light from another star, will emit specific wavelengths of light. This results in an emission or bright line spectrum. The temperature of a star does affect its color. We'll learn more about this later in the unit. The nebula seen here is rich in hydrogen gas. The bright line, or emission, spectrum shows the fingerprint of many other elements. The plot of wavelength versus intensity shows the amount of each element present. Hydrogen, by far, is the most abundant element. The atoms of these gases were excited by absorbing energy from hot young stars in a cluster behind it. They re-emitted the energy in the wavelengths shown here. In the graphic on the lower left, some photons of specific wavelengths are absorbed. This produces the dark lines in the spectrum of the star on the right. The pattern of lines in the spectra from stars and planets allow astronomers to determine what these objects are made of. Astronomers compare the spectrum of a star to the spectra produced from gases in the laboratory. Matching an element's spectrum to the spectrum of a star tells us that that element is in the star. Temperature influences what lines are seen in a star's spectrum. The coolest stars here are M stars. They show prominent lines for titanium dioxide that are not seen in a hotter O star. The compound titanium dioxide dissociates, or falls apart, when heated strongly. You should be able to tell from its apparent and absolute magnitude that Sirius is closer than 32.6 light-years from Earth. It is actually only 8.6 light-years away. In class, we would have gone over these for practice. The answers would be revealed one at a time, allowing you the opportunity to practice what you learned. An object's spectrum is affected by its motion. If it is moving away from the observer, its light is shifted towards the red end of the spectrum. If it is moving towards the observer, its light is shifted towards the blue end of the spectrum. This also works with sound. A car horn changes pitch as a car approaches you, and then passes you by. You can calculate the speed at which a star is moving away from us using Doppler shifting. In this graphic, the spectrum of Arcturus is compared to that of the Sun. You can see that Arcturus's spectrum has been shifted to the right. We can use the amount of this shift, and a bit of math, to calculate the speed at which we are moving apart. Nucleosynthesis is the formation of new larger atoms by the fusion of smaller ones. Stars can do this, building up from hydrogen, atomic number 1, to iron, atomic number 54, in their cores. Where do you think heavier elements than iron come from?